In this video, we're going to be looking at how to quantify energy, or how to come up with some mathematical formula to allow us to calculate how much energy there is in a system and how it changes from one type to another. And we're going to do that by starting with this idea of work. Work, again, being the change in energy of a system due to external forces interacting with that system. So here's our first sort of mathematical representation. Work, capital W, is equal to the change in the energy, where this E is standing for the energy, the total energy in the system. So the sum of all the different kinds of energy. That's our general definition of work, but there's also a mathematical definition. If you remember thinking about momentum and change in momentum or impulse, we said was the area under the force time graph, or force times change in time for a constant force. Work is sort of similar to that. Work, mathematically, we define as the area under the force displacement graph. So this is sort of similar to impulse, except instead of thinking about how long we're pushing something time-wise, we're thinking about how far are we pushing it for. So the work done by an external force, which we'll call F, over some displacement, or displacement change in position, delta x, can be found by the area under the force displacement graph. So if I'm pushing on something with a constant force as it moves a certain displacement, here's my constant force over a displacement, that area would be the work done. So in this case, my nice constant force, the area is just got a rectangle, base times height. I would say the work is the force times the displacement. Now we'll talk more about why I'm putting this x here. This is to show me that the force is in the same direction that the object is being displaced. So this is just how physicists have determined how they're going to calculate work. Work is the area under the force displacement graph for a constant force that is the size of the force times how far the object's been displaced. These are in the same direction. Now we can use this to come up with some formula for these different kinds of energy, because we know work is the change in energy. Now that we have a way to mathematically calculate work, we can talk about what that looks like for coming up with ways to calculate different forms of energy. All right, calculating energy. We'll start with kinetic energy. Usually just use the symbol K or EK for kinetic energy. Take a scenario, let's say I've got a person and they're just pushing a box on a frictionless surface. Box has mass, they're pushing it with the force F. Let's say initially it's not moving, but they push on it as it travels some displacement, delta x. And we know that from our experience with forces, as they push on this box, it's going to get faster and faster as they push it along this distance. So we know it's gaining kinetic energy. Well, how much? How can we calculate that kinetic energy? Once it's over here, we know kinetic energy is related to speed. So maybe we figure out, okay, how can we relate this to the speed, how fast it's moving? In this case, I'm saying velocity. We'll see that ends up being speed in the end. So how could I relate these quantities? I've got force and displacement. I know that's my work, and I want to somehow relate it to velocity. I'm going to go back to an old friend. This is our fourth kinematic equation of motion. So I see it's got some things in it that I want to relate here. I've got my velocity, I've got my displacement. If I can get force in here, then I can start talking about work. I can start talking about energy. So to do that, I have to see, how can I get force into this equation? I've got A, I've got acceleration, so that makes me think of Newton's second law. Think about the forces on this object. We got gravitational up, the floor, gravitational down, the floor up, and then we got this force that I'm pushing with. And we know Newton's second law tells me A is the sum of the forces. In that case, that's just F, because I just have the one unbalanced force. All right, so I could plug this in here. Oh, we said it was at rest, so we'll get rid of that initial velocity, make things easier. 2 F over m delta x. And I might notice, looking at this, that right here, F times delta x, well, that's work. So let's get that by itself. So I want to get rid of this 2 and this m. So I'm going to multiply each side by m over 2. That's going to cancel this 2 with this 2 on the bottom, this m with this m on the top. Instead of writing m over 2, I'm just going to write 1/2 m vf squared equals f delta x. All right, well, this is the work. This is the change in energy. This is how much I changed the box's energy by, because we defined work as F delta X, and work again is the change in energy. So I can say here that my change in energy is 1/2 mvf squared. And if we think, all right, how much energy did the box start with? If we drew an energy bar chart for this box, we would have said, well, it has no energy at the start. It's not moving or anything. At the end, we would have said it had kinetic energy. Well, this is how much energy I changed it by. I changed it by 1/2 mv squared. So how much energy does it have? It must have started with nothing. My Apple Pencil seems to have failed me. Let's pause for a second. All right, we're back. So I had no energy. I now have kinetic energy. This is how much my energy changed by. So I'm going to say this must be my kinetic energy. That's how much kinetic energy I gave the box. So we now have a formula for kinetic energy. 1/2 m, get rid of that f, v squared. All right, great. So now we're up to two ways to mathematically represent energy. We've got work. We now have a way to represent kinetic energy. Up next, let's look at gravitational potential energy. Which we could see represented as UG or EG, depending on who you're talking to. All right, what situation we're going to look at here is let's just look at an apple. This apple is some height above the ground, because we know if we lift things up, we say that they gain gravitational potential energy. We'll say the ground is when we have none. You always have to say when you have what height you have no potential. Usually it makes sense to make the ground. All right, well, let's think about this apple. Let's say the apple is our system. Let's make the apple our system. What forces are acting on our apple if we just drop it? Well, that's just the Earth. Earth has that gravitational force pulling down on that apple. And how big is that force? You know, it's m times g, the gravitational constant. So if I think about work, if I think about the change in energy, of the apple as it falls here, how much does it change its energy by? Well, we have the force, and we have how far it falls, h. So its energy changes by mg, that's the force acting on it, times h. Well, notice here I wrote these as x, but we can think of them as y, right? It's pulling in the y dimension. It's traveling this displacement of h and the y. What matters is these are in the same dimension, in this case, the vertical. All right, so the change energy here was mgh. So this is where our potential energy came from. We know that this mgh is going to turn into kinetic. So it has this potential, turns into kinetic. mgh, that's how much potential it had. So we can write, here is our formula for gravitational potential energy. Another way to think about this one is to think, well, how much work would I have to do to lift the apple up to this height? Well, I'd have to push up with at least mgh to beat this gravitational force. I'd have to push up with mg the other way. I'd have to do it for height h. I'd have to do mgh work to give it that much gravitational potential energy. All right, the last one's a little bit more complicated. Our elastic potential, or spring potential. Energy. So this could be U elastic or U spring, or I guess E elastic or E spring. Maybe this is why this is like using U so they don't have situations like E elastic. Who knows? All right, so let's think about a horizontal spring and maybe I'm pushing some box up against that spring. Springs, we know, are a little tricky. We can't just use F delta X. So when we looked at F delta X, we were talking about, this was for a constant force. Maybe we should make a note for that here. For a constant force, F. And we were able to do just force times displacement to get our work, our change in energy. We know from our investigations of springs, however, that the force of a spring depends on its displacement. It's not a constant thing. We know the spring equation, F equals K delta X, where this K, remember, is the stiffness of the spring, or the stiffness coefficient, or sometimes it's called the spring constant. So we can't just do F times delta X here, but we do have a recognizable shape. Work is the area here. So our change in energy, or our work, you'll notice me using those interchangeably because that's work just means the change in energy. It's just the area of this triangle. So we have a triangle instead of a rectangle. That complicates things slightly. 1/2 base times height. Well, our base is the displacement, and our height is the whatever our final force is, F. All right, but again, this force was changing. So we know at the maximum it was just K delta X. So let's just put that in there. So here I'm just substituting in my spring equation from my lab to figure out, okay, what is the force at my maximum here to find this real height. And now we have, okay, we have 2 delta X's, 1/2 K delta X squared is the change in energy. So to stretch a spring, some delta X, this is how much energy I would need to use. If I was starting from not stretched at all to stretched, because we're taking the whole area here. All right, so that's our last. Energy equation. You'll see that this does depend on what kind of spring you use, as well as how much you stretch the spring. So both of these determine how much energy you get. Just like if we look at gravitational potential, it depends on how high the object is off of our 0 point and the mass of the object. And then kinetic energy, we can see, depends on how fast the object is going. You'll notice that this gets squared, so it doesn't matter what direction. It's actually just dependent on the speed, how fast, because a negative number would turn positive. And the mass, so objects with more mass and objects with more speed have more kinetic energy. Similar in some ways to momentum. All right, so yeah, now we can do some situations. We have the classic one situation we've looked at many times a couple months ago. I just dropped something from a height of 5 meters. Say it's a 2 kilogram apple, and I want to know how fast is it gone right before it hits the ground. And we could do this with kinematics. We know the acceleration and free fall and so on. But let's do it instead with energy. At the top, I would say this apple has, feel free to pause and try to do this yourself first if you want. Say it has UG, and at the bottom, I would say that UG has become kinetic energy because it's right before it hits the ground, right above the ground, has no UG left. So that would be my two energy bar charts here. We could say, here the energy is going if we wanted to. Earth to the apple. As the apple gets faster, it's my system. Energy flow diagram. And usually we'd leave it there. Okay, we'd say, all right, 4 bars, energy is conserved. Now we have some numbers we can do here. We can figure out how much energy we have here using our formula. All right, so we got 2 kilograms, 10 newtons per kilogram. We're assuming we're on Earth, per usual. 5 meters. This ends up being 100 newtons times meters. So this is our unit of energy. It's kind of weird, a newton times a meter. If you look at, we said work was force delta X. So there we see it again, a newton times a meter. There's a unit that physicists replaces this. We just call that the joule. 100 joules, where a joule is a newton times a meter. And a joule is the unit of energy. It's named after James Joule, some old dead white dude who figured this out, I guess. All right. Well, conservation of energy says 500 joules, I guess this is plural, 100 joules of energy beforehand as potential. I now should have, this is my initial, this is my final. Here we looked here, and here we looked here. I should now have 100 joules of kinetic energy. So how fast am I going? Here's my formula for kinetic energy, 500 joules. So I again know the mass was 2 kilograms. Little math here. No, that's a coincidence. I end up with 10 meters per second. Because 2 times a half, I got 1. Take the square root. End up with 10. The unit going from joules to meters per second might seem a little bit weird. You have joules equals, we had 1 kilogram times v squared. So we had joules divided by kilograms. A joule is a Newton times a meter. And Newton, if we think about A equals F over M, and we rearrange that to MA equals F, a Newton is a kilogram meter per second squared. So we can say, all right, kilogram meters per second squared times meters over kilograms. Cancel the kilograms. Meters times meters is meters squared over seconds squared. So this 100 joules per kilogram becomes 100 meters squared per second squared equals our V. V squared here. So, and then we take the square root, we get meters per second. So you'll find with energy, the units are kind of crazy, but they end up working out. All right, cool. Do lots of practice with this, don't worry.